start now. Uh, is my screen visible, Vaishak? Vaishak, is my screen visible? Hello, Vaishak. You can see my screen, right? Okay, okay. So, last week we faced a few issues related to ADC. Um, it was related to AD con 1 register configuration. We chose different configuration. So, I will show you which one was that. So, in AD con 1, we choose this option. Okay, so instead of that, uh, I chose this one. After that, it started working, but still I am facing some issue. For that, we need to debug ADC in deeper. So we need to know how what value is coming out from the ADC after conversion. For seeing that, we need to use debugger. Okay, right now I don't have any debugger. So there is one more method to see the internal registers and internal variable status. For that we need to print the internal variable. For this purpose, we need to use serial port of microcontroller. Okay. So today, yesterday in the WhatsApp group, I told that we are going to do the second project, but we will postpone that. Instead of that, we will start learning a new interface called serial port interface. So serial port interface, I will explain the basics of communication a little bit. So we have two kind of communication in electronics. One is serial communication. One is serial communication, and another one you already know, that is parallel parallel communication. So in serial communication, we will be using only one wire. Okay, one wire for communication, but in parallel we will be using multiple wires. So parallel communication, you can see the communication data lines would be more. Input to the data lines would be more. It will start from D0. If it is an 8-bit communication, it will be till D7. But in serial communication, we will have only one data line for transmission. TX, for transmitting, we will have only one data line, and for reception, we will have another data line. So packets would be going like this, one by one. Okay, first maybe LSB D0 will go, at the end D7 will go. So there should be some mechanism called clock also. Okay, so there would be some clock pin. available for serial communication. So based on the clock, this TX and RX will be sampled. Without clock, there is one more communication. Without clock, if we are communicating, we call that communication as asynchronous communication. In communication, serial communication, there are two types, synchronous and asynchronous communication. So our microcontroller support both these synchronous and asynchronous communication. Why we are discussing about communication peripheral is because just now we interfaced the ADC. Okay, so so this was the customer requirement. Customer was requested they need a fan working based on temperature sensor. But we wrote a code and the code is not working perfectly as we expected. So we need to debug the code. For that, we need to know the internal value which is coming after the conversion. For that, we can use one method called we can use debugger, microcontroller debugger hardware, and we can see the values. But I don't have hardware right now. For that reason, I am using a serial uh, another method called printing the internal registers using serial port. So I will update this circuit for this purpose. Okay. So I am going to add a serial monitor here. So we have in this particular software we have one particular thing called virtual terminal. So I am adding that virtual terminal here. Why it is not allowing me to add it? Let's just close this circuit and open it. Okay. So RX I am going to connect with the TX and so this is the serial communication pin. Just now I draw right CX and RX pin. Serial communication for sending the data out we are using TX pin, and receiving the data from outside world we are using RX pin. Okay, so these are the two pins um, which we are going to use when we use GSM modem, GPS, any other serial peripheral we have. We can use these two pins to communicate with that peripheral. So here we need to configure its baud rate. So I wanted 9600 baud rate only. So this is the baud rate of this peripheral. You can treat this this device as a modem or computer. So whenever microcontroller sends some data, it will be displayed in this screen. Okay, there would be some screen popping up. I will show you. So when you hit play button, you can see one virtual terminal popped up over here. So here you can see the data coming out from the microcontroller. I wanted to print ADC value of, after conversion. Okay, so this is what I wanted to do. Okay, so Just we will go back to data sheet. We need to configure our serial port. As we configured our ADC, we need to configure our serial port also. So we will go to that section. So this is addressable universal synchronous asynchronous receiver transmitter use USART. Okay. So they are telling universal synchronous asynchronous transmitter module is one of the two serial IO module. One is serial communication interface SCI. So they are telling they have two modules. One is I square C. So other one is USART. Okay. So the USART can configured as a full duplex. Full duplex means you know, right? You can send and receive simultaneously. Okay. So while sending also you can receive data. Just like our mobile phone, we can talk parallelly you can listen to. The USAT can be configured as full duplex asynchronous system that can communicate with the peripheral devices such as CRT, personal computer. Also, you can make a project using TX and RX pin, like you can transmit your um, physical data to computer. There you can write some other codes using either LabVIEW, Visual Basics, Python to read the serial port of your computer, personal computer can display the data, temperature, humidity. Also, you can control devices using that also. We will do such projects. We will discuss such project. Maybe we will do also. Okay, what it is? Okay, communication devices such as A to D, D to A, integrated circuit, serial prompts. So, whichever peripheral using TX and RX as its communication pin, you can interface with the PIC16F877A microcontroller. Okay, they are telling it can be configured full duplex, asynchronous master, synchronous master, synchronous slave. Okay, and SPEN bits of TRIS7 have to be set in order to configure pins RCCX. Okay, they are telling about the register. There are two register which need to configure. In ADC we configure two register, right? ADC, ADCON 0 and ADCON 1. Here it is TXSTA and RCSTA. We need to do, we need to configure two registers. One is TXSTA and another one is this one RCSTA. One is TXSTA, transmit status and control register. Another one is RCSTA. RCST. So yeah, we will begin with configuring TXSTA. So I am typing TXSTA. Here we need to find out the hexadecimal value. So yeah, before that, you need to know how UART asynchronous. We are going to uh, configure in this mode, okay, asynchronous full duplex mode. So based on the requirement, you have to configure. So right now, I need this mode. So that's why I am configuring in that mode. So you need to know the timing diagram of asynchronous communication first. So I will draw the timing diagram. So keep in mind this is TX pin timing diagram. So TX pin will be idle. Idle means 5 volt. If no communication is happening, the pin will be in 5 volt. Then start bit is um, high to low communication, high to low transition of that particular pin. Okay, so this is called start bit. Then there would be 8 data Okay, 8 data. If it is high, this would be the case, or if it is low, it would be in the low situation, low state only. Okay, so next one is low, 0, then etc. Seventh bit, sorry, eighth bit is 1, eighth bit is 1, and it will continue to be in the high state. So this is the last bit, this is the zeroth bit. Okay, this is the seventh bit. So total, how many bit would be there? 8 bit would be there. Okay, so last bit is called stop bit. Okay, so stop bit. So then it will be in ideal position. So this is the uh, data. This is the timing diagram of UART communication. So 5 volt will be the ideal condition. I mean, the TX pin will be always high. TX pin will be always high when there is no data communication happening. Um, then suddenly, if microcontroller sends something, it will go low, and it will be treated as start condition. Then it will start sending its bytes in bit format, bits in one by one. So it will send accordingly. If it is 0, it will be low. If it is 1, it will be high. So 0 means 0 volt, 1 means 5 volt. Okay. So this is the data which it is sending. At the end, it will send stop bit. Okay. So this is how it is working. So you need to know that before going into the register. So what is TX90? TX90, they mentioned it. It's ninth bit of transmit data, can be parity bit. We are using only 8 bit, so we can ignore it. So this is for some other communication scheme where parity bit is used. So we can treat this particular bit as 0. So TXSTA first bit position is 0th bit position is 0. Okay. Now TRMT, transmit shift register status bit. So whenever you see a name called status or a term called status, you need to know it is a monitoring flag. Okay, monitoring flag means there won't be any effect if you write something over there. So if you write 0 over there or 1 over there, it won't affect any functionality of the microcontroller or the UART peripheral. Okay, so it is a monitoring flag. So what they are telling, if it is 1, TSR is empty. If it is 0, TSR is full. TSR means transmit shift register. If you want to learn deeper about this UART, you can always go down and you will see one block diagram. Here you can see what is TSR. TSR is a transmit shift register. Whenever you want to send a particular data, you are writing that particular data to TXREG register. Then it will reach to TSR register. Then it will shift one by one through TX pin. So you have TX pin, right? So you can see that TX pin over here. TX pin is getting its data from a pin buffer. That pin buffer is getting data from TSR register. Okay, so whenever you want to send some particular data to through this pin, you are pushing that particular data to TXREG register. Then it is going into TSR register. There are some other flags also, transmit enable flag, TX90. So this is that TX90. If you are transmitting ninth bit data, it is you need to enable it. Then only the ninth bit will be added over here. So this is the thing. Uh, to learn deeper, you can read the data sheet much more deeper if you want. So TX90, we are not transmitting the ninth bit data over here. So we will keep it's 0 and TRMT. TRMT is the monitoring flag. We don't have to do anything over that particular flag. So we are writing 0 over there. Okay. Now the second bit is baud rate high select bit. Okay. So asynchronous mode you can keep one if you want high speed, 0 if you want low speed. So there is a baud rate kind of thing. So baud rate means the communication speed they are mentioning. Baud rate means bit per second. Okay. So I explained we are transmitting data like this. Okay, one by one. So here transmitter is transmitting data and receiver should receive it, right? So in the other side, receiver will be receiving data. The data will coming like this, okay? High low based on the data packet. So receiver has to identify the data, right? Start bit, stop bit, and the in between data bits. Okay. So how they are identifying? They are identifying the data. Identifying means sampling. So they need to sample it to differentiate start bit, stop bit, and the in between data bits, right? And they need to. So suppose I am sending a 0xAA value, 0xAA value over here. Receiver should receive 0xAA, right? So they need to sample it properly because there is no clock. There is no clock. I mean, TX line, only TX line is using based on a particular mechanism. Based on a particular mechanism, they are transmitting this data. That is called baud rate. So transmitter is transmitting data in a non-speed. Okay, in a non-speed, and I mean the receiver is known. The speed of the communication is known by the receiver. I mean, receiver already know that this transmitter pin is transmitting at a speed which is known by me. Suppose here our speed is you know already, right? Here our baud rate is 9600 bits per second. So RX already know that the transmitter is transmitting at a 9600 baud rate. Okay. So receiver already know that transmitter is transmitting at a 9600 baud rate. So receiver has to sample it with that speed. Okay. An example I can tell. So we have one um, lorry over here and a person standing here and one person is there inside that lorry and lorry is filled with so many watermelon. Okay, so this guy who is standing in on top of the lorry is unloading the watermelon and this guy is catching that watermelon. So they need to be in synchronization throwing the watermelon, right? So he need to throw the watermelon and this guy has to catch it. So this receiving guy is already aware of the throwing speed of this person standing on on top of the lorry. Okay, so if this guy who's standing on the lorry is throwing at a faster rate than the than this guy is catching speed, watermelon will get spoiled, right? It will fell down, it will go somewhere. So both need to be in a good understanding at the throwing speed. So similarly here, both are in an understanding about the communication speed. Here, this particular particular TX pin is transmitting at 9600 and this RX has to sample at 9600. So you are configuring the baud rate select bit BRGH. So we can keep, we are using asynchronous mode, right? Asynchronous means there is no clock. So we can keep this 0 if it is low speed and if it is high speed. From where will you will get identify whether it is a high speed or low speed. For that you have to scroll down. So this is the BRGH pin, BRGH flag. So if you keep 0, it means low speed. Okay, in asynchronous mode, baud rate calculation would happen like this. Okay, so 9600 equal to frequency of oscillation. Frequency of oscillation means at what rate this microcontroller oscillates. I am going to keep it 11.0592 because it is a this crystal is um, going to help to get 9600 baud rate accurately. Accurately means with very less error. Okay. So here the calculation. Here we have a calculation. They have given frequency of oscillation. You can keep 11.0592 megahertz, 11.0592 divided by 64 plus x. So x means we have a particular value we need to write at a particular register called SPBRG. Wait, serial port rate generator. Okay, so we have one more register. This is the third register we need to configure in order to get the communication SPBRG. So SPBRG value we will get out of this. So either you keep 0 or 1. The thing you are going to change is that your calculation method will change. So baud rate calculation, in order to get 9600 baud rate, you need to find the value of x. Okay, you need to find the value of x. That x you are going to get by using this equation if you keep 0 over there. Okay, if you keep 1 over there, your calculation equation will become like this. Okay, so it is based on the crystal frequency. So right now I am using a lower, comparatively lower frequency, that is 11.0592 megahertz. So I am going to keep BRGH equal to 0. So BRGH you know already where it is. We are discussing TXSTA. BRGH you can see here that BRGH is 0. Okay. So here I need to keep okay, we will type in our code only. So first value was 0, second bit position, I mean first bit position was 0, and third bit position BRGH is also 0. Now fourth, zeroth, first, second and third bit position. Third bit position is unimplemented. Okay, so unimplemented means 0. You can keep that bit position also 0. Now we have sync. What is sync? SYNC UART mode select bit. We need asynchronous mode. For that you can keep 0, or else we need to keep 1 if you are using synchronous mode. In the beginning itself I told that we are using asynchronous mode. So what we have to keep? We have to keep 0. Okay. Now what is that? Transmit enable with TXEN. If you want to transmit a particular data, you need to keep 1 over there, or you need to switch off this transmission, then you can keep 0 over there. We need transmission enabled for, so we will keep 1 over there. Understood, right? TXEN is a particular flag. You can see it inside that block diagram. So everything is connected. Okay, so if you want to know a peripheral in detail, you need to read the data sheet in detail. So here you can see TXEN. If this particular bit is enabled, and based on the baud rate, there would be some shifting clock will be generated. Okay, so based on this TXCN. If you enable it, then only you will get a output over here. You can see an AND gate present here. Based on the SPBRG clock, this AND gate will generate another clock if TXCN is enabled. Okay, output clock. Same clock will get here if TXCN is enabled. You know the working of AND gate, right? Both input should be 1 in order to get the output 1. So TXCN is enabled. Okay, fifth bit position is enabled. We need to enable it. And sixth bit position, they are telling 0 means selects 8-bit transmission, 1 means select 9-bit transmission. Our transmission is 8-bit. Okay, so we need to keep 0 over there. So TX9 flag we need to set 0. 0. Now CSRC, clock source select bit. In asynchronous, they are telling don't care. In synchronous, they are telling something which is not relevant to our current discussion. So I am skipping that portion. So asynchronous, it is don't care. Okay. So don't care means you need to keep 0. So this is the value which we got. This is 2. So this is the first portion is 2 0x0010, right? That is 2, and the remaining portion is 0. So we can write like this. So this is the value which we are going to write in TXSTA register. Okay, 20. Only transmission is enabled. TXN is enabled. I'm just writing a comment here. Enabled. Asynchronous. Asynchronous and 8-bit communication. 8-bit communication. Now we need to configure one more register called RCSTA. So this embedded system programming is and driver development is almost register configuration and manipulation. Okay, so this is what we embedded engineers always do when there is a new peripheral and new device to be interfaced with our microcontroller. Based on the system requirement, we are doing the configuration. So RCSTA, yeah. RCSTA equal to, we need to repeat the same process. Read all the bits features. RX90, what they are telling, RX90, ninth bit of received data. Okay, so we will get ninth bit if transmitter is transmitting ninth bit. If transmitter is transmitting 1 as ninth bit, we can see 1 over here. If transmitter is receiving 0, you can see 0 over here. So this is a status kind of flag. We don't care about status kind of flag. So when initialization, okay, so we are doing initialization of serial port now. So it is 0. And OERR, it's a flag over an error bit. 1 means there is an over an error. I mean, suppose a TX is sending data and RX is receiving that data, but the controller didn't perform any um, controller actually didn't receive that particular data. Okay, I will explain what it is. So what actually happens is that you have your microcontroller, right? Okay, so microcontroller, you can call it, right now I am calling it as a CPU. inside the microcontroller we have this UART peripheral, right? So this is UART, and UART has two pins, TX and RX. So CPU has to monitor this UART. It is a supporting peripheral of CPU. Like as I said in the beginning class, we have many peripherals. One among them is UART. So suppose a data is coming inside the microcontroller. You need, after getting the data, UART peripheral will tell to CPU that I received a data through interrupts or some other flags. Okay, so it is the duty of the CPU to receive that data and store it somewhere else, because we only have two buffer to store the data. If both the buffer fills, then that would be an error. It won't be able to, our serial port won't be able to receive the third data. Okay, so there would be a missing of data if we won't receive that, new data and keep it separately. So it is the duty of the CPU to keep it in a safer place. Okay, so overrun error bit will set if there is an overrun. Overrun means we are getting multiple data and CPU is ignoring that. So overrun error will get set. So overrun error is a monitoring flag. So we are least bothered about when we initialize it. So we are keeping it 0. Next flag is FERR. What is FERR? Framing error bit. Suppose when there is some noise kind of thing, a framing issue would be there. So we have a frame, right? We have a frame of data. So here we have start bit, stop bit, in between we have data bits. So if something happens to this frame, it this framing error flag will get set. There is some issue, we need to tell the receiver, sorry, transmitter, to resend that particular data. So this is also a monitoring flag. We are least bothered about that flag when during initialization. Okay, so 0. Next one is ADDEN, address detect enable bit. So asynchronous mode 9 bit, it should be 1. Okay, so ours is 8-bit communication, so there is nothing to do right now. Disables address detection, all bytes are received, and ninth bit can be used as parity bit. So ADDEN, we are not using it. Address detection, we are not using that scheme, so we can keep it 0. Next, continuous receive enable bit. In asynchronous mode and synchronous mode, you can see two kind of configuration here. If you are in asynchronous mode, this is going to happen. So we are in asynchronous mode, right? Oh. So we are in asynchronous mode. So 1 equal to enable continuous receive, 0 equal to disable continuous receive. We need to receive the data continuously from the transmitter, then we need to set it 1. Okay, so we need a continuous reception, so we are setting this particular flag 1 because we need to receive continuous data, that's why. Next bit is SREN, single receive enable bit. In asynchronous, they are telling don't care. So don't care is always 0. And ninth bit receive enable bit. We are using 8 bit, so it is 0. And serial port enable bit, entire serial port. In ADC, we have AD on register, right? To enable, to turn on the ADC. Here also we have one particular register called SPEN, where you can uh, enable or disable the serial port to, in order to save the power. Okay, so every peripheral inside the microcontroller uses power. So if you enable it, it will start consuming energy. So in order to save that particular energy, you need to turn that particular peripheral off. So for that reason, there is always any enable on off register for all the peripheral. So we need to enable it. in order to start the communication. So we are setting it 1. So the last bit, I mean seventh bit is 1. Eventually we are going to get a value like this 0x90. This is the value which we have to write it right into RCSTA. So what and all are there? Yeah, serial port enable, um, continuous receive enable. These are the two things which we set. Okay, remaining all are monitoring or status flags. So we configured RCSTA and TSSTA. Now, if you read the data sheet, they are telling you need to configure, you need to find out a particular value. Okay, so this is the equation to find out the baud rate. Okay, I'm going to write it over here. Copy. This is the equation. We know the values also, right? Baud rate we need is 9600. There are many baud rates. Okay, it is an assignment kind of thing. You find out which are the available baud rates in serial communication, UART communication. You can find many baud rates. This is the common baud rate where many devices are marketed with the default value. 9600 is the default value for the many modems, many UART based communication devices. And you know the frequency of oscillation also, it is 11.0592, and you need to divide, you need, I am submitting all the values to this particular equation. Okay, 64 x plus 1. Okay, so we need to find out the value of x over here. Okay, how can we find? We need to do some mathematical operation here to find out. We need x equal to, so 11.0592, you can write it like that, 11.0592 into 10 raised to 6. Okay, 10 raised to 6, 10 raised to 6. Just a second, I am doing some paper calculation over here on my desk. After that I will tell you how x can be calculated over there. If someone online who already know how value of x can be calculated, just ping me over the chat. Okay, so here we have 9600 in the left side, and in the right side we have 11.0592 into 10 raised to 6 divided by 64 into x plus 1. 64 into x plus 1 equal to 11.0592 into 10 raised to 6 divided by 9600. So x plus 1 equal to 11.0592 into 10 raised to 6 divided by 9600 whole divided by 64. Now x equal to 11.0592 into 10 raised to 6 divided by 9600 divided by whole divided by 64 minus 1. Okay. So I am just opening my calculator. So our crystal frequency 11.0592 into 10 raised to 11.08. Okay, 6 into 10 raised. Okay. Minus 1. Okay, so value of x we are getting at the end is 17. So we need to rearrange the equation. So here we are getting 17 as the result after rearranging. uh, Wait, I will tell you how I rearranged it, or if you already know, you already learned mathematics, right? So based on that you can calculate. So what I did is I just moved entire 64 plus 1 towards left side. So we have 64 plus 1 in the left side. Yeah, like this. So at the end, if you properly shift values with our requirement, you will get a value equation like this: x equal to our frequency of oscillation FOC divided by baud rate bracket, frequency of oscillation divided by baud rate divided by 64. Okay, entire value you are keeping it inside a bracket, then minus 1. Okay, so this is the equation. After rearranging, you will get a equation like this: x equal to frequency of oscillation divided by baud rate divided by 64 minus 1. Okay, or else you can multiply frequency of oscillation divided by into 64 divided by baud rate minus 1. Okay, you can always do that math over here. So x equal to 17. So we have one particular register called this one, SPBRG. X equal to value in SPBRG. The value will be from 0 to 255. So based on the SPBRG value, we are going to get, see, We have many chart over here. They calculated it for you. You can see if you are soldering a 20 megahertz crystal with your microcontroller, you can see SPBRG value for different baud rate. Okay, 9006K baud rate, they are using 31. If you are using 20 megahertz, okay. So 10 megahertz, you need a 1200 kilo baud rate. You need to keep value of 129. So you can use the chart, or else you can use the equation to find out the value of x. Okay. So here in this chart you can see SPBRG register. See, SPBRG register is responsible for baud rate generator. So we need to load that particular value. So yeah, this is what I am going to do as the third step in the initialization of serial port. So SPBRG equal to 17, right? This is the value which we got after calculation. So 17. Now our serial port is ready for communication. Now it is our duty to send a value. Okay. I am going to write a function already written over here. Send it to modem. Okay. Send it to modem means anything modem or PC. For your understanding, I will modify this to here PC. Okay. Keep just think like this is a PC. Okay. So I am I need to send a value a character a. Okay, so I am sending that character like this. So after initialization, uh, if button am equal to pressed, I need to send a particular thing. Send it to PC. Button equal to press, send it to PC a, character a, capital letter a. So what will happen here is send it to PC is a function which can receive a character, a value, only a single value, single 8-bit value. So here you can see this function has an argument. So the argument type is char, unsigned char, and the name is value. So value will receive the character. Okay, and txreg register will be written with that value. You already know what is txreg register, right? Txreg register is the register which receives the value from the controller, microcontroller. Okay, here microcontroller CPU is the CPU. CPU is the one who writes the value to UART. UART is a peripheral. Okay, so here CPU is the one who writes value to TXREG register. Here I am telling with the help of my program. I am telling the CPU to write to UART's TXREG register with the value. Okay, so TXREG register will be updated with the value. Value is A now, and it will wait. A polling kind of mechanism over here. It will wait while TRMT equal to 0. You know what is TRMT register. So TRMT is a flag which resides in TXSTA register. Okay, so inside TXSTA register you can see this TRMT flag. I already explained what is TRMT. Once the communication is complete, it will be 1. Okay, so once communication is complete, it will become 1. So what we are doing while TRMT equal to 0, continue. We are telling the processor to wait, CPU to wait until TRMT flag sets to 1. So the communication has to complete. I mean entire start bit, data bit, stop bit, then the ideal condition. Ideal condition means the TX pin will be in 5 volt. At that time, TRMT flag will be 1. Till that time TRMT flag will be 0. So this is what is going to happen. Let's see whether our code is working fine or what. I am building it. So what should happen? After pressing the button, we need to see A transmitting over there. Okay, we need to receive A. Let's load the program. I'm just checking whether, yeah, it is updated code only. Yeah, A is coming. See, I will clear it. I will stop it and run. I am going to remove this button. That is our auto manual switch. So in this screen, you can see the virtual terminal. You will see A only after pressing this button. See, A is coming. A means auto mode. Okay. So with the help of this function, we can print the result. Okay, we can print the result after ADC conversion. We are getting a result, right? So I am confused that the result is not proper. So um, I am expecting some other value, and the controller is giving some other value. So I need to know what result is. So with the help of send it to PC, I have to send the result. Okay, so it's already 10 o'clock. We can wind up for today. Next class we will complete that ADC discussion with the help of this UART communication. Okay, so see you next week. So we finished UART interfacing. Yeah. See you then. Bye bye.